oxygen flies so high. All could use a doctor. Who's sick? Who's next? Never you mind. Death professor, electrified. My love is better. It's crystallized. So mine could be the diamond fused with who's next. This is beginning to feel like the dawn of the loser forever. This is beginning to feel like the dawn of the loser forever. This is beginning to feel like the dawn of the loser forever.
You told me I would never see you walk away. Said you'd never break my heart, never leave me in the dark. I guess there's just some promises you shouldn't make. Should've known from the start. Now I'm in the dark. Show a little love, shine a little light on. Show a little love, shine a little light on. Show a little love, shine a little light on. Show a little love. I'm in the dark. Can't see, can't see, can't see. Just feeling my way back to you. I can't feel, can't feel, can't feel. Reach out and show a little love. Shine a little light on. Show a little love. Shine a little light on. I'm in the dark. Show a little love. Shine a little light on. Show a little love. Show a little love. Told me I would never see you go astray. Said we'd never be apart. Never leave me in the dark. I guess there's just some promises you shouldn't make. Should've known from the start. I'm in the dark. Can't see, can't see. Just feeling my way back to you. I can't feel, can't feel, can't feel. Reach out and show a little love. Shine a little light on. Show a little love. Shine a little light on. I'm in the dark. Show a little love. Shine a little light on. Show a little love. I can't see, can't see, can't see. Just feeling my way back to you. I can't feel, can't feel, can't feel. Reach out and show a little love. Shine a little light on. Show a little love. Shine a little light on. I'm in the dark. Show a little love. Shine a little light on. Show a little love. Show a little love. You don't like roller coasters. How could you ever love a girl like me? I took you to the end of my street so you could see my bones. A couple of promise to you. Our stars came in a packet of two. She's walking to you. She's dying to be by your side. She's walking up to you.
Is this on? Can you hear me? Can you hear me? Yeah.
I'm going to have you put those slides up.
Yeah, I think so. Okay, good afternoon, everybody. By my clock, we have 4 p.m., and I'd like to make sure that we try to stay on time. I understand it's Wednesday afternoon, and everybody's been very busy so far, so we're going to try to keep the schedule. My name is Nicole O'Shea. I'm from the University of Notre Dame, and I'm here organizing this symposium along with John Grieco, my colleague, who's sitting in front row. And today, I'm assuming most of you are here because either you've been involved in the past or you are now currently interested in spatial repellents. And so the goal of today's symposium is to really give you an insight as to where we are, where we came from, and where we anticipate we still need to go in order to have these products potentially be used for public health purposes. One thing I will say, I was walking with Emo Kleinschmidt. I lost him somewhere in the audience, but I'm a little bit out of breath because, thank you, Emo. This room was a little bit difficult to find, I think, and it was, I think, quite clever of Emo to say, well, whoever's in this room is really dedicated to coming to this session, so thank you so much for taking that time. I'm only going to take 2 slides here, and a minute for 2 slides. This is just an overview of where we've been with spatial repellent category. Back in the 1950s, there's been scientists that observed how mosquitoes behaved in response to certain active ingredients that had been used for malaria mosquito control. And some of those observations included behaviors such as moving away from a home that had been treated with IRS chemical. So this is many decades ago. And then as we pass through this timeline, which is very brief, we've actually had some very rigorous clinical trials, some prevalent studies to show how mosquito coils, which is one example of a spatial repellent, can actually help to reduce infection of malaria in different cohorts of populations. And the first was by Nigel Hill back in 2011 in China, and the second was performed by Dr. Din Sayafruden, who you'll hear from also later this afternoon. And both of those studies helped to serve as some basis of proof of concept that spatial repellents indeed have some level of public health value, but there needed to be more evidence in order to have that be confidently endorsed. So in 2012, there was a convening at the WHO to develop guidelines for spatial repellent testing in anticipation of this category being formally approved. We're not there yet, but there was anticipation by WHO that it could happen. And I have to thank Morteza Zayam, who really had the foresight to make that document be put in place well before there was a recommendation, so we can go through as a community and amend it as we gather more data. And so we hope to have that happen in the next year or two. And then finally, we have some current ongoing clinical trials using a spatial repellent product, which I won't say anything about now because Amy Morrison and Din will say more about that in their presentations. Okay, so we have a lineup here of very prestigious speakers, friends and colleagues. I thank you all for taking the time to be here today. John Grieco from the University of Notre Dame will be talking about some effects of mosquito behavior after exposure to some spatial repellent chemicals. And then Tom Scott will talk about, well, what are the criteria and some of the gaps that we need to fill in order to endorse this category for public health. Amy will talk a little bit about some of her ongoing findings from the clinical trial in Iquitos, Peru, which is still active at the moment. Din will talk about some of the recent findings from his trial in Indonesia. And then we'll wrap up with Susan Van Hol, who's with the Catholic Relief Services, and get a perspective about an implementer and a procurer of these products and what are some of the ways in which she, as a procurer, her perspective sees as a value to this category in her work, and as also what are the challenges that we still have to overcome to actually implementing these products. And then we'll end with a panel session. So I would like to ask, in order to keep on time, that you hold your questions till the end of all of the speakers' presentations. And then we'll have about 30 minutes to have an open discussion on either their specific topic, or we also have some questions for the group in case we don't have questions coming from the audience. Speakers, there's going to be a 3-minute warning. You've got 15 minutes. And Thomas is our audiovisual leader in the back, so if there's anything that happens with your presentation, please reach out to him. Thank you. Without further ado, John.
Thank you, Nicole. So Nicole has asked me to kind of give an update about where we sit with spatial repellents. Originally, we had a concept of what spatial repellents were. We had the thought that they acted in a certain way. There was a limit as to what they could do. And over time, a number of groups, including ours, have been doing research in the lab, in the field, and finding that the actions of these chemicals that we call spatial repellents go far beyond just breaking the human vector contact from a behavioral standpoint. There are a lot of actions that occur that may impact on every aspect of the life stage of the mosquito. So I'm going to be covering a little bit of that, but what I want to do is start out by kind of going through where we started out. And I remember in the early days, 20, 25 years ago, there were heated discussions about what are the actions of these chemicals? What are they doing to the mosquito? And people would argue that there's exciter-repellency, all these different actions, but all centered around either movement away from a host source without making contact, which we called spatial repellency, contact irritancy, which was more of making contact with a surface that had the chemical, the mosquito became irritated or agitated and flew away, and then we looked at toxicity. So early on, we limited it to just those three main behavioral actions. And that led to us developing these crude models. If we were to have a house, we protected it with a spatial repellent, we could exclude a large number of mosquitoes and basically create a bubble around that house, protecting everybody within that structure. Anything that did come in that broke through the spatial repellent barrier would then maybe make contact with the surfaces, become irritated, and leave before feeding, and that would be the ideal situation. Then we would have toxicity where the mosquito would become overcome by the vapors, or they would leave and die, or some of them might actually survive, which would be the least acceptable situation. So with that in mind, we were called to WHO to develop the spatial repellent test guidelines. And in doing that, we had to come up with a number of assays that we liked to use for selecting out these various endpoints, entomological endpoints. But we struggled with what the true definition of a spatial repellent should be. And we settled there on a large number of behaviors, but anything that basically prevented biting. So a reduction in biting was what we were really looking for. But a lot of things can result to a reduction in biting, including toxicity. So that's where we ended with these test guidelines. But if you look at that, the current definition is focused on one point in time in a very crude life cycle of the mosquito. But and it's at a single point in time. But over the years, what we've seen is that all of the publications that have been generated, we're increasing the number of publications, and all of that data is showing us is that this is not a single point in time event, that it extends beyond the initial exposure, that we're getting post-exposure events that are disrupting a lot of the life cycle of the mosquito. So this is a diagram of the transmission dynamics David Smith et al. Published, and you can see the complexity of it. You've got seasonal patterns, you've got egg laying, you've got all the different components that go into the transmission dynamics of some of these diseases. And as our view of the transmission dynamics of these diseases change, so must the view of these various chemicals that we're using and these various tools that we're using to interact with various aspects of this diagram. We need to look at spatial repellents from the standpoint of not being a sole point in time exposure. We have products now that we put out, and they're exposing the mosquitoes on a nightly basis to a spatial repellent dose. So these are sublethal concentrations. We're looking at various aspects of the life cycle that we're targeting that we didn't target initially with our spatial repellent concept. So if you look at some of our early work, we developed an assay. We could tease out doses that were considered spatial repellent, that were not killing the mosquito, and then it moved into a toxic level where we were killing the mosquito. But within that range of doses that actually did not kill but repelled, you might have impacts on emergence, mating, sugar feeding, all of the life strategy characteristics of a mosquito. And those are the things that we wanted to start to look at. How would these behavior-modifying compounds impact on these other aspects of a mosquito's life cycle? So some of the early work by one of our graduate students, Joe Wagman, showed that it wasn't an initial impact on the mosquito. If you exposed a mosquito to a repellent, it just didn't fly away. That impact lasted far longer than just that initial exposure to the compound. So he found, what he tried to do was select mosquitoes on day 1 and show that he could repeat that on day 2 and then follow it up with a day 3 trial. So the repellent effect occurred on time 0. He saw an attenuation of that result 24 hours later. When he repeated with the same mosquitoes 48 hours later, that repellent effect returned. So that got us thinking, was how long were these effects actually impacting on the mosquito? So we set up a trial where we exposed mosquitoes. put them in a feeding arena, and looked to see at various time points, 1 hour, 3 hours, 6 hours, 12, 24, to see how long could we actually disrupt the feeding behavior of the mosquito. And what we found was that similar to what Joe found, was that out to 24 hours, we were still having an impact on those mosquitoes by seeing a reduction in feeding. It was only a 12% reduction, but it was still significant as compared to control. So these reactions that we're seeing are going far beyond just that initial point of contact of the mosquito with the repellent. Then we started to look at other things. We started noticing in our test arenas that the mosquitoes were showing some form of agitated flight. They were moving much faster, they were buzzing around, they weren't resting as much. So in the early days, we set them up on flight mills. We would expose the mosquito, attach them to a pin, and then allow them to fly around in these flight mills. We would register flight distance, flight speed. And what we found was that a mosquito that interacted with transfluthrin actually flew farther, but that was a result of them flying faster. These mosquitoes were much more agitated. They were flying. They were just buzzing around and not being settled. But we also found if we looked at it 1 hour post-exposure, that trend reversed. And then 3 hours as well, that trend stayed the same. So what that tells us is that somehow those mosquitoes, the flight reserve, the energy reserves of those mosquitoes are actually being depleted, and they're actually slowing down. They're almost exhausting themselves with this agitated flight. So nowadays we can do a lot more. We can do a lot more detailed studies because we've got behavior tracking software. The top study, Phil McCall's work, where they're doing, the flight around a bed net, how many contacts it makes, so they can monitor resting, they can monitor flight activity, all the different various endpoints that we couldn't measure with just the flight mill. In the bottom is the work that we've been doing and looking at different arenas with treated versus untreated mosquitoes. And again, we can look at number of turns, we can look at time resting. And the same thing that we saw in our flight mill is repeated here, where you see the transfluthrin exposed mosquitoes actually show a much higher level of activity. They're not resting as much. They're just buzzing around a lot more. They're making a lot more turns. So again, showing that kind of exhaustive behavior, which is impacting on the mosquito. So we're seeing this hyperactive response with transfluthrin. It's exhausting the reserves. But one of the questions that we had is this actually impacting on the survival of the mosquito? And what we found is if we treated cohorts and carried them out for the full length of the lifespan of the mosquito versus a control population, we saw that with Aedes aegypti, we actually saw a reduction of 4 days in life as compared to the control. And with Anopheles gambiae, we saw a 3-day reduction in the lifespan. Now, it doesn't seem like much, but when you give this data to the modelers, it has a huge impact on the transmission potential for these mosquitoes. So when we think about spatial repellents, we need to go beyond that initial single-point contact of the mosquito with the repellent in the huts. Christopher Bibbs this year actually published some data on some great studies on the egg production of mosquitoes. He found that if you expose mosquitoes to transfluthrin, Aedes aegypti, you actually had egg collapse with the resulting eggs. For the ovaries, he found fewer numbers of eggs were actually produced in the ovaries, and those that were produced showed an increase in melanization, which actually reduced the egg viability. So there's a lot going on with this something like transfluthrin, and he even stated in his paper that this is a single point contact with transfluthrin. These chemicals are out there in the environment. They're making multiple contacts. So this may actually be accentuated with some of the strategies that we're using today. We carried out a study looking at the potential for disrupting ovipositional attraction. And our assumption was that if you expose mosquitoes to transfluthrin, they would be confused and they wouldn't find the containers that held ovipositional attractants. But what we found was the opposite. The mosquitoes actually went to a greater extent to those containers with the attractants. And our assumption here, we're still teasing this out, but our assumption is that there's a heightened response in the mosquito or a heightened sensation in the mosquito to olfactory cues such as ovipositional attractants. The other thing that we're looking at here that we've actually noticed in recent years is a phototactic response, a higher sensation for light. And so mosquitoes are actually going more preferentially to light sources. This may actually help us with traps. So the light traps that we're using, could we implement this in a push-pull strategy? So if you look at what's been going on, we're starting to see a lot more emphasis on these post-exposure effects, kind of delineating what needs to be done in terms of our gaps in our knowledge around spatial repellents, in terms of diversion, formats for chemicals, and we're building that breadth of data around what needs to be done if we're going to have it truly a spatial repellent compound for WHO recommendation. But in conclusion here, some of the things that we're talking about, we really need to consider. Most studies have been done with a single dose, and some of the products that we're using now in the field are 1 month in duration. So if a mosquito cannot obtain a blood meal on night 1, what happens on night 2? Does it come back? We're suggesting probably not. There seems to be that delayed response in coming back for a secondary feed. So even if it comes back every other night or every third night, it's still picking up multiple exposures to these chemicals. And we're seeing from some of the other studies that that's impacting greatly on egg production, egg viability, just all of the factors that we really consider as key transmission issues with these vector-borne diseases. Most of these studies have been done with transfluthrin. This is a volatile pyrethroid. So we know that it's going to have an impact as a toxicant at some level. But what happens when we're looking at things like PMD, other things that we consider as repellents? Are those going to also show similar types of trends? Or are they going to show completely different types of impacts on the vector behavior, all of these other endpoints that we've been measuring? So we need to do much more studies on these other types of active ingredients. The broader vision, we need to look at how these different types of interactions are complementing or interfering with some of the other technologies that we're using. Like I said, phototactic response, we're seeing some issues around increased attraction to light. Can we utilize that for push-pull systems? Can we use the ovipositional attractant data that we have about increased attraction to make some of our traps, our ovitraps, better for our GATT traps, increasing trap collections? And then what are the considerations that we need to have about how do we evaluate these tools now? We developed these guidelines, and we had a small set of tools that we were using to evaluate them. Do we need to increase that suite of tools to take into account all of these other aspects? And the other piece that I didn't put up here was field evaluations. All of this has been done in the laboratory. How do we capture these endpoints in the field? This is not an easy situation to do. You know, we've been talking about semi-field situations, looking at different types of enclosures, but there are limitations to those because then airflow is different, release points are different. You're impacting on all the behavioral pieces that you don't want to alter when you're trying to evaluate these tools. So I think that's one of the challenges for everybody moving forward is how do you capture these other endpoints in the field when they're so much easier to capture in the laboratory. And this is my last slide. So this was kind of a recreation of that crude probability model. And what we're hoping that we can do with these new evaluation tools is to be able to extend that line on the bottom. We're looking at movement away, attraction inhibition, feeding inhibition, but now we need to look at maybe ovipositional site disruption, other types of things that we need to be adding to that bottom line to really get a much better view of what spatial repellents are doing to disrupt vector transmission. And I think that's my last slide. Okay, thank you.
Great, thank you, John. And as I asked, we like to hold questions until the panel discussion. So next I'd like to ask Dr. Thomas Scott to come on up to the podium and discuss the next steps and criteria in spatial repellents.
Is this working now? The microphone working? There we go. Okay. Nicole asked me to give you an overview of what the process would be of assessing a new product like a spatial repellent. So I'm going to do that from the perspective of the WHO criteria. So I'm going to start with sort of a general presentation. If you had a new product, what would the process that you would need to go through, what would that be? And I will eventually get to the point to show you how spatial repellents fit into that. So vector-borne diseases are a huge, it's a growing problem. 80% of the world's population is at risk. 17 to 20% of the estimated burden of global diseases is attributable to vector-borne diseases, and there's over 700,000 deaths. There's some common tools that we've used over the years for malaria, things like insecticide-treated nets, indoor residual spraying for arboviruses, space sprays, and larvicides. But we need new tools. There's considerable new problems that are challenging us now, like expanding vector populations, transmission in urban settings, or if we want to try to eliminate a disease. Insecticide resistance is a growing and significant problem. And there's new and emerging arboviral or vector-borne diseases. So these challenges have stimulated researchers and people to develop new innovations. I've been doing this for over 45 years, and what we're going through right now, I'm seeing the most innovation in vector control than I've seen in my career. So it's really an exciting period of time. Well, we need to have some independent way of assessing these products. What effect do they have, and in particular from a public health impact in terms of reducing infection and/or disease. So countries that would uptake these new products have some sense of what they can get if they decide that they want to purchase them and use them. So WHO is in the business of developing an evidence base so that they can inform their member states on how they could use these products most effectively. And the Vector Control Advisory Group, or VCAG, is an advisory body to WHO. And they deal with new tools, technologies, and approaches for vector control. And what they do is they help them to assess the public health value of these new interventions, and then provide some guidance on how they could be best used or deployed. Now VCAG defines public health value as proven protective efficacy to reduce or prevent infection and/or disease in humans. As vector biologists, for a long time, we've really primarily focused on showing that there was an entomological effect. But what we're really interested in is preventing disease. So now what the advocacy is for is to go beyond entomological impact and show that there's a reduction in infection or disease in humans. VCAG is a cross-department collaboration at WHO. It includes the Global Malaria Program, the Department for Control of Neglected Tropical Diseases, and the WHO pre-qualification team for vector control products. And this is a figure that shows the flow. If you submit an application to VCAG or to the WHO, what the flow is. So I'll walk you through it. So initially, you'd interact with the Secretariat. You'd fill out an application, and that would go to a pre-submission coordination team, and that's made up of the Secretariat. So the members of VCAG don't participate in this process. So it's people at WHO, at pre-qualification, global malaria, and neglected tropical diseases, and they make a call as to whether or not what you're submitting fits into a product class for which there already exists a policy. If there does, then you go up to this part of the figure. The pre-qualification team, which is noted here with this yellowish color, would then assess the product safety, quality, efficacy, and an additional thing that they're going to be doing is inspecting the manufacturing facilities to ensure quality of the product. Then after the safety, quality, and efficacy is confirmed, there would be a product listing. So that's if you fall into an existing product class. If you don't, if you really have something novel and new, a different approach, then you have a different path forward. VCAG is shown here in blue. So at the same time, it would go to the pre-qualification team and do the same thing you did up here, but it would also go to VCAG. And VCAG would assess the public health value. Then after they had done that, they would make a recommendation to the advisory groups to the Global Malaria Program and Neglected Tropical Diseases about what the policy would be for that particular product. Then these two things would go over it and you'd get a listing. So depending on whether you have a product that has a policy existing for it or not, has a big influence in terms of what path you would follow forward. Let me go back here. So if we just look at this part of it, there's some more details here that deal with assessing the public health value, what VCAG does. There's 3 steps. The first one is to, in essence, propose a concept. So in your application, you would make the case that there's a credible case that this would have an impact on disease, and you define some of the key things that you would measure. And you do that working together with the Secretariat. The second step would be laboratory, semi-field, small-scale field trials, essentially dealing with entomological outcomes. So you'd be doing the sorts of things that John's talking about, and when we have a question and answer period, I'm sure he could give examples of the kinds of things that they did in this process. But the idea is a proof of concept entomologically. So you show that, for example, if you have a repellent, that you can repel the mosquitoes, and that's consistent with reducing the risk of people getting infected. And then the third step is a randomized control trial to demonstrate the efficacy of the product, that it is going to in fact protect people from infection or disease. So that's a proof of concept epidemiologically. So that last step was informed to really a pretty significant degree by this article. So Steve Lindsay, Emo Kleinschmidt, who is here, and Wilson, took the lead in doing a review of the literature in terms of what existed as far as assessing public health impact of vector interventions, and then talking about what we could do to improve the state of that art. And quite frankly, it wasn't very good. And so this is if you're interested in this sort of thing, it's really an excellent article. It's a primer on how to properly do control assessments with a public health outcome for vector interventions. This is what I refer to as the stoplight pyramid, which talks about different types of trial designs that could be used to gather a public health impact. And this figure came out of that article, but we had an expert advisory review group last year that refined it a little bit. And basically what it is, these on the top here in green are a go forward. The yellow is proceed with caution, maybe under some circumstances, and red is that it would not be acceptable. And this is based on a methodology that is for assessing the efficacy or studies that are designed to provide information for developing policy or guiding recommendations. Randomized control trials are considered the tops in terms of their quality because of the low risk associated with selection bias. And then you can use them to do efficacy trials. So under very well-controlled circumstances, you can get a measure of what the effect size is. What's the difference between the treatment and the control group, which would be different than an effectiveness study, which would be more realistic in terms of an operational delivery. Now, there was a pair of studies that were published in The Lancet in 2014 that really bemoaned the quality of clinical trials that were being carried out. So we in vector control don't necessarily need to feel so bad. They were saying this across clinical trials with vaccines and drugs. But it is an opportunity to, following these sorts of guidelines, to increase the rigor of the studies we carry out, and therefore the quality of the information that we get that can help to inform policy and inform the countries that would use those interventions. This is a list of the 18 different product classes that WHO is currently reviewing, and I'll walk down through them with you. There are several different insecticide-treated nets, not with a non-pyrethroid, a pyrethroid plus a non-pyrethroid, pyrethroid and a growth regulator, a synergist that essentially makes a resistant mosquito susceptible, and a supplement that is treating certain parts of the net versus others. Spatial repellents, that's what we're talking about here. Attractive targeted sugar baits, primarily for Aedes. Outdoor spray for residual killing of sandfly vectors. It's a sort of a barrier idea. Repel and lure. There's a couple different kinds of traps. These are primarily for Aedes. So these are adulticide overtraps and then auto-dissemination with pyriproxyfen. There are 3 different approaches with genetically modified mosquitoes. The Oxitec OX513A, these are essentially sterile. It's a sterile insect release technique. And then there are 2 that are using CRISPR-Cas9, so a gene drive system. One of them has to do with population reduction, so it makes the mosquito sterile, and the other one is an alteration of the population to make susceptible mosquitoes, susceptible to the parasite, resistant so that they can no longer transmit it. This is a sterile insect technique that also includes Wolbachia, so in addition to using radiation to sterilize them, if any females were to escape, they would not be able to get infected with a virus. This is for Aedes. And this is the Monash program with Wolbachia, rendering them refractory to infection and transmission of viruses. This is a systematic treatment of cattle. This is essentially for leishmaniasis. And then lethal house lures. This is the Eve tube concept for control of malaria. So there's 18 different products here. The ones that are highlighted in red are at stage 3. So if I remember correctly from the slide before, I should have noted that there's 4 that are in stage 1, 2 in stage 2, and 12 out of the 18 that are in stage 3. So we really have quite a few of them that have moved far enough along that they are either currently in the process of doing those stage 3 epidemiological trials, or they're in the process of planning to do them. Spatial repellents is right here. They have actually 2 phase 3 trials, one for malaria and one for dengue. If you're interested in reading about these, after each VCAG meeting within a couple of months, there's a report published. This is the 8th report that meeting took place in May of this year. There's an overview of the products, the list that I just went down with more detail. And there's a document that gives an overview of the standard operating procedures. So if you did submit an application, what you could expect the process to be. And all of them can be found at this website. The last thing I wanted to mention to you, if you're not already aware of it, is the Global Vector Control Response. This is a program that was really quite rapidly developed. Steve Lindsay and Willem Takken and Tessa Knox were the principal architects of this. But last year in May, it was unanimously approved by the World Health Assembly. And the goal of this is to reduce the burden and the threat of vector-borne diseases by effective, locally adapted, and sustainable vector control. And at least for us in the dengue field, that's a different approach. It's not just one thing everywhere. It's really understanding your particular location and designing a particular approach for that set of circumstances. This is the temple that is a diagrammatic representation of what the program is. Up here at the top is effective locally adaptive control. There's pillars of action, foundational concepts, enabling factors. But the one thing that I wanted to point out, and this is text that I took out of the report on these foundational features, both elements, both of these A and B, are required to ensure maximum impact of sustained vector control by using an evidence-based approach to planning and implementation. That means we have to have the information from the level 3 or the stage 3 trials, the epidemiological trials. Otherwise, we're not going to be able to tell people in a clear way what kind of effect they can expect in terms of reduction in infection and disease. And I will stop there.
Great. Thank you so much, Tom. Okay, so now I'd like to invite Dr. Amy Morrison to the podium to speak about her ongoing trial there in Iquitos, Peru. Okay, countdown, 3-minute warning, laser.
Okay, and do I?
Yeah, Thomas is going.
He'll do it.
Yeah, there we go.
Okay.
Should be
All right. Well, thank you, Nicole. So basically, I'm going to just tell you about the ongoing RCT that we're conducting in Iquitos, Peru, which will be wrapping up in January. So maybe a year before we have, or end of 2019 before we have results, but we are really getting to the end. And I start by telling you a little bit about Iquitos. It's located in northeastern Peru, and it's a socio-epidemiological island. It's about 380,000, it's probably up to 400,000 now. And it is only accessible by air or river travel, which makes it a unique location for dengue transmission studies. The transmission history is well documented by the U.S. Navy in the city. They had their first introduction of dengue virus in 1990, and we've been working on cohort studies since 1999. So we've been able to characterize transmission dynamics effectively. We have been conducting entomological monitoring for that entire time, and we have a pretty long history of doing vector control efficacy trials, although I'd say this is actually our second RCT. Let me tell you a little bit about the design of this study. We have 26 clusters of approximately 150 houses. That's how they were designed. The city is divided into 34 Ministry of Health zones, and we formed our clusters by selecting blocks at random in 13 of those zones, building a cluster of about 150 houses. So that runs from about 1 to 6 city blocks will comprise a cluster, depending on the local space. And then we would essentially move the furthest location within that Ministry of Health zone to initiate or to build the second cluster. So we had two clusters within 13 different MOH zones. And you can see those locations. Let's see. You can see each of the different colors. This stippled area is another ongoing cohort study being carried out in Iquitos at this time. Essentially, oops.
Yep, maybe he can advance too if it doesn't work.
Okay.
Thomas, can you advance, please?
Thank you. This is just some photos of the device. It's actually an 8.5 by 11 plastic sheet coated with transfluthrin. And the approach that we've taken to deploy them, there needs to be a shield to cover every 9 meters squared. So our team, and I think I have some photos of this later. Go ahead and advance. There we are. Has a pretty unique way, and I'll show that in a little bit later. But as Tom pointed out, the endpoints for this trial are epidemiological. So we're measuring dengue virus or Aedes-borne virus transmission in 2 ways. We essentially have a cohort. So we invite everyone living on those blocks to participate in the study. And essentially all they have to agree to is a visit 3 times a week by our staff to ask if somebody has a fever. If they have a fever, we consent them to give a blood sample, and they would give us a second blood sample 14 to 21 days later. And this way we can identify clinically apparent Aedes-borne virus disease. Second, we have a subset of that group of children, pediatric cohort, where we take blood samples essentially annually. And then we can do a microneutralization test and identify seroconversions, which will include inapparent infection as well as apparent infection. So this is essentially two measures of transmission. The denominator for the active surveillance component is very large. We have about 17,000 people under surveillance. There's been a fair amount of turnover. And this cohort is about 2,200 people. So it's a much smaller denominator, but it's two distinct forms of measuring transmission. At the same time, we continuously monitor the Aedes aegypti population. Baseline surveys, we look at both larval indices and adult indices, but all subsequent surveys essentially are using a Procopec aspirator here. Well, actually, I have to click to vacuum out adult mosquitoes. And this is in our hands, a very effective way to measure the Aedes aegypti population. Now, let me show you a little bit about how these shields are deployed. We have a team of about 5 guys who are amazing, but they can measure the front side of the house, and essentially for anything up to 3 meters, they'll run an elastic line down the middle of the house. Up to 6 meters, it would be 2 elastic lines down the full of a house, because in Iquitos, most of the houses don't have closed roofs. They're open eaved. So we can just literally hook up the elastic line the whole length of the house, and then we would start on one line and just using photo check clips, hook them up on the top. Now I've got some more pictures to sort of show this. So you can see sort of, and then we just make a little cylinder, clip it with the photo clip, and this is all kept track of in a cell phone application. So we know how many shields are in the house. We have an application to ensure that we have appropriate spatial coverage, and we can monitor replacements of those shields so that we need to replace them every 2 weeks. So 1,700 houses every 2 weeks. It's been a pretty big job. And here's just some more photos of the shields. And it really only takes less than a minute to do the replacement, as long as we have access. This is some pictures of the adult mosquito aspirations. You can see here, we use a ComCare, which is a commercially available service that uploads the data to the cloud. It's secure, and it allows our personnel to collect this very repetitive data over time. In addition, we use the ComCare app to monitor our surveillance visits so that we can actually document the fact that we are knocking on those doors 3 times a week and have solid denominator data for our infectious disease rates. And I think we've got a couple of the people who've built these apps here, so after I can introduce you to Anya and Will, who have done this. So just to give you, I can't really reveal too much. We can't break the code. That's something I also should explain, that we essentially receive 26, or not 26 boxes, hundreds of boxes with 26 different numbers. And each number corresponds to a cluster. And this is a double-blinded study. So 13 of those zones get essentially a blank. It has a solvent on it. And the other 13 clusters get active ingredient. And what you can see here is we'll show you that we have managed to identify active disease. We had a Zika outbreak during the startup of this study. So this is either excellent news or it could have just waited a few more months, but there was a lot of transmission. And I think this will give us the power, this will help give us the power we need to evaluate this tool. And again, I can say these were the cases that occurred during the actual deployment. So we took that first blood sample, deployed the shields, and then we started following our cohort. And then these are cases that we've picked up since then. And you can see this over time. In terms of our longitudinal samples, we are currently taking our third annual bleed. We've completed 2 annual bleeds, and this shows a little bit of the evidence. We will go back and look at every dengue serotype and Zika for all paired samples, because again, we want to identify a seroconversion, which means somebody without antibody and they develop antibody during that year period. And in terms of the entomology surveys, as of August, we'd conducted around 87,000 surveys, identified, and this was just in the baseline surveys here, these 19,000 containers, and up until now we've collected almost 150,000 adult mosquitoes. And I just pulled new data, so this is really an underestimate. We've collected a lot of mosquitoes, and we've actually done 60 rounds of these 2-week follow-up collections. What I did here is just to, this was earlier on in a preliminary analysis, but the blue bars represent the baseline surveys before deployment of the shields, and then I just collapsed survey data for post intervention, and this was really in the first few months after deployment. And what's encouraging is this decrease. This isn't necessarily what we would expect, but it is encouraging that you see that trend. And this is just some of the baseline people demographic surveys from the baseline surveys. Let's see. Could you advance? There we are. Another important thing that okay, good, no. Another important aspect of this RCT is to be able to monitor adverse events, because this is a chemical product and we have the opportunity to measure this in both the control and treatment areas. And we've had to be sort of, I don't want to say clever, but we've had to take a number of approaches. One thing we do, and we're required to do in a human use study anyway, is report all deaths. And we've had 185 since the study began. And we really haven't, this information is sent to a data safety management board to see if they find any link to the shields. People do die in these cohort studies. We also monitor dropout rates, households that actually, ask to be removed from the study. And in this case, we've only had 5 reasons that were given that were associated with a health effect. We actually had 26 reported adverse events, and this is a case of sort of an allergy, dry mouth, itching, or skin irritation, headache. And all of these, again, need to be reported on a quarterly basis to the Data Safety Managing Board. We also have some vasovagal responses when we take blood samples, and these were distributed across 11 clusters. Advance, please. Okay. The other really important issue is maintaining coverage. If we don't have the product in place, we're not protecting our population. And Will Elson has done a lot of work. Could you advance it to, again, you can sort of see the structure of the cluster. And this is some data where, again, we have about 1,700 houses mean per round. You can see we've maintained about a coverage rate of 82%, which I think for those of you involved in vector control, not bad. And it takes a lot of effort. And I think I'm running out of time, so I'm going to advance. And this just illustrates from Will, again, our essentially the temporal pattern of coverage. It took us a while to get things deployed, and we had a little chaos in the beginning, but then we really hit our rhythm. Advance. We've also monitored insecticide resistance, so we have what was called a genetically diverse laboratory strain that we can use as a control that was developed from 10 colonies coming from different spatial areas in Iquitos, including where the clusters are. And these are maintained in our laboratory in Iquitos. And then after a year, we pulled the eggs from each of the clusters. They were pooled with the help of our data safety managing board. Again, we have to always think about blinding and maintaining our lack of knowledge of which clusters have the shields and not. But the take-home message here is that we are seeing some development of resistance in bottle assays, and so we'll do this again at the end of the study. And next slide. And finally, another thing that we're doing is a self-administered shield perception questionnaire. It's a small 12-question survey that we hand to residents to ask them, do they feel more or less mosquitoes? But the idea, again, is to blind us from their responses. So somebody teaches them how to use the app, and there's always some kid who's very good at it, so we can get it done. And also, this is a way to see how people feel about the product. And what you can see is that about 60% of the people answering the survey indicate that they feel like they're being bitten less, and about 52% feel that there's fewer mosquitoes. 40% say they'd pay for repellents, but 83% would recommend them. And again, just discussing this with the population, there has been a pretty good uptake, but it is labor intensive, the switching out. And I just stop there, thanking our research team. They're really amazing, and our collaborators at the Naval at NAMRU. Without them, this couldn't be taken care of. So I'll stop there.
Thank you. Thank you, Amy. Again, please hold questions until the panel discussion. Dr. Din Sayafruddin now to the podium, and he'll be discussing his latest activities in Indonesia. Great. Okay, Din, forward, backward, laser, and here's your time. Okay, I'll give you a 3-minute warning.
Thank you very much, Nicole. My task actually to report about the RCT that are now done in Indonesia. So designing an RCT is, especially for spatial repellent, as previous speaker mentioned, is not an easy task because it is not a drug that directly prescribed into people who is observed, but this is a new device. This is applied to the environment where the population settle. So the project goal, as Nicole mentioned before, that to measure the impact of the spatial repellent on the malaria efficacy, so protective efficacy, and also whether this protective efficacy that is gained correlate directly with the entomological correlates. So in 2008, our group at the Ekman Institute, in collaboration with colleagues from US number 2, successfully mapped malaria in one particular island here, Sumba. The island of Sumba is located in the down south of equatorial line. The climate is really equatorial, and we identified one or two villages in the south